Welcome. In this video, we will find the electric field at distance z above the midpoint between two equal charges q at distance d apart. This is a very common example for when you're just starting out with electric fields for point charges. And it is incredibly important that you understand every single part of this. This is a problem that will let you understand the formula for the electric field and everything that comes afterwards, because afterwards it's the exact same thing but different geometry. So if you understand this, you'll be in a very good footing to understand the rest of electrostatics. Okay, so how do we solve this? How do we begin? Well, first of all, of course, we need to understand the drawing here. Let's understand the situation. So what we have is we have a Cartesian system already chosen, right? I chose the 0 to be in the midpoint between both of my charges. Of course, this doesn't really look like the midpoint because I'm not good at drawing, but I promise it is the midpoint. And we know that these charges are a distance q apart, and that is why this distance here is d over 2, and this distance here, I promise, is also d over 2. Now, this is a very important thing whenever you are in electrostatics. The first step is going to be to set up a coordinate system. So coordinate syst. Okay, so set up a coordinate system. That's step number 1. You will always have to do this, okay? Once we have done this, let us now write down the formula for the electric field, because that's what we're looking for, right? So we know that the electric field for a point charge is going to be, right? So 1 over 4 pi epsilon 0. This is going to be now multiplied by each one of our charges. So let's just say that this is the electric field for, some general I charge. So this is qi. And then we divide this by the distance between this I charge and our point of interest, and then we multiply by the vector, the unit vector that connects them. Again, you could be using, that's squared by the way, you could be using the different notation where you have our vector instead of our hat, but I really like this notation better, but it is the exact same thing. Okay, so now that we have this, we need to just quickly go through what we have and what we do not have, and also draw into our drawing those quantities that we are looking for. So first of all, this is a constant, so no need to worry about it, so check. The individual charges we are given, we are told they are q. We don't know the numerical value of q, but it is a given, so check. Now this unit vector and this distance, we do not know. We do not know this, and we do not know this. So where are these in the drawing? I encourage you to pause the video and think about it, because this is where you get confused. If you cannot identify where these vectors are in the problem, then you will not get any further. Okay, so this is where people get confused. So the vector, this vector, is the one that connects each one of our charges to our point of interest, which is point P right here, right? It is a distance z above our 0, right? So that is the point that we care about. So this entire vector right there, that vector is vector r. Now notice this is vector r, not r hat. R hat, of course, goes in the same direction and has unit length 1. So r hat also goes in that direction, okay? And if we call this just 1, right, just to make them different, this would be R1, R1, and similarly, this vector right there would be R2, and thus this thing right there is R2 hat, and this distance, the distance is going to be the modulus of R2, and well, similarly here, that distance is the modulus of R1. So now we have identified every single quantity that we care about, even though we haven't found them yet. But at least now we understand the situation a little bit better. So once we have those quantities, to find the total electric field, all we will need to do is add up the contribution from these electric fields. Okay, that's everything that we will have to do. All right, so how do we actually begin? Well, let's just choose any of these charges to begin. I will choose one, right? 2, of course, being this one. It doesn't matter which one you choose, but it is always good to pick one and go about it, right? You need a direction, otherwise you won't get anywhere. So in our list, what we have done so far is write down E, then identify the unknowns, and now we have to begin solving. So how do we go through this? Well, let me just do the drawing once again. So now we have our 0 here, this here is going to be Q, and the other Q is right here. Now our point of interest, it is in the z-axis. Notice that I called my axis X and Z. Of course, you can call them whatever you want, X and Y, Z and Y, X and Z, it doesn't matter. And our point P is somewhere over there. So let's try to find this vector R, because once you have vector R, right, once you have vector R1, you can easily find R hat and also the modulus of R. So some people here get very confused, right? How do we find this vector? And they get very confused. What is my recommendation? Think of what a vector is telling you. A vector tells you how to go from one point to the other. Okay, so there are many ways in which you can try to find this vector. And the way I like to do this, especially when a vector is not located at 0, right? This is where like teachers like to say, oh, well, R1 is simply a vector R minus vector R1 prime. And then you have to find each one of them, this being a vector R and this thing being R1. And this is correct. This is very much correct. But I believe that it is not the easiest and most intuitive way, because if we think about what a vector is, again, a vector tells you how to go from one place to the other. So R1 starts out here and it ends up there. So I ask you, how do I get from here to there? Well, first of all, I need to walk in the negative x direction for a distance of d over 2, right? I'm going to get rid of the minus to not confuse you. So first, I need to go minus d over 2 in the x hat direction. And then once I'm here, I need to go up a distance z, right? We are told this is a distance z, which is going to be our variable. We can put this closer or further away. And then I need to go up a distance z, so plus z, in the z hat direction. And there we go. This is vector R1. And notice that now we can easily find everything else, because what is the modulus? What is the modulus of vector R1? Well, we can just look at this image right there. I'm going to get rid of this line to not confuse you. To find the modulus, which is the length of this thing right there, we see that this is a right angle. So we can use the Pythagoras theorem here. So that means that this side squared, so d over 2 squared, plus this side squared, which is z squared, is going to be this side squared. So the modulus of this thing squared. But of course, if you just want to find the modulus, you take the square root, and we end up with the square root of d over 2 squared, squared plus z squared. All right. So now we have found our vector and its modulus, but we don't have our hat, right? Because again, what we are trying to do here is we are trying to find every single thing in there. We have already found R1, the modulus here, but we haven't found yet the unit vector. So now let's keep in mind that the unit vector, what is it? Think of its definition. If you cannot think of the formula, think of its definition, right? That is the whole point in physics and mathematics. We need to think logically. It's not about memorizing. So what is a unit vector? It is a vector that goes in the same direction as, that other vector, which in this case is r1, but it has a magnitude of 1. So this is the exact same vector as r1, so minus d over 2 x hat plus z hat, except that it has a magnitude of 1. So how can we turn this into something of magnitude 1? Well, we divide this by the magnitude, right? So we divide this by the magnitude. Now let me maybe write this out. So r1 over the modulus of r1 is r1 hat, right? The unit vector. So we already found the modulus. So this is d over 2 squared plus z squared. And there we go. This is the unit vector. So now we are in a position to put everything together into our formula for the electric field. So the electric field due to charge 1, right? The electric field due to charge 1, this is going to be, well, let's see, 1 over 4 pi epsilon 0. We already knew that. Then we have our q. q1 is simply q. And then we divide by the modulus. So time q divided by the modulus, which is going to be the modulus squared. So we get rid of that square root. So we get d over 2 squared plus z squared. And then we have to multiply by r hat, which is exactly there. So there we have minus d over 2 in the x direction plus z hat. And we divide all of this by the square root of d over 2 squared plus z squared. Now notice that we have the same thing here and there. So we can, of course, multiply them. We have the one, this thing there is to the 1 power, and the other one is to the 1/2 power. So if we have a to the 1 times a to the 1/2, well, you add the exponents and you get a to the 3/2, right? In this case, a is d over 2 squared plus z squared, right? So we get this thing there to the 3/2 power. Okay, so that is the contribution from our first charge. Now, what about the other charge? Well, in the case for the other charge, what we have is going to be basically the same thing, but let me show you anyways. So now I'm going to just flip some of these things. This is still z. This is still d over 2. But now we're looking for this vector, which is, as we said, vector, r2. Okay, so how do we find this vector? Again, think of the definition of the vector. The vector goes from one place to the other. How do we go from here to there? Well, first we can go d over 2 steps in the x direction, right? So r2 vector is going to be d over 2 steps in the x direction. And then we go z steps in the z direction. So as you can see, it is basically the same thing as r1, but it doesn't have this minus sign. All right? And from here, we can find everything else, right? You can find its modulus, right? We can use the Pythagoras theorem here, just as before. So r2, I will go a little bit faster here. So r2, this is going to be the square root of d over 2 squared plus z squared. And the r unit vector is going to be this thing divided by this thing. So d over 2 x hat plus z hat, and divided by the square root of d over 2 squared plus z squared. Okay, and now we have to plug this back into the expression for the electric field due to this charge. So the electric field due to this charge, well, what is it? Well, this is the same basically as before. So 1 over 4 pi epsilon 0 times q divided by, here we get d over 2 squared plus z squared, and then we multiply by the unit vector, which is d over 2 x hat plus z hat, and then we divide all of this by the square root of d over, that looks like an A, d over 2 squared plus z squared. And again, we can combine this and this. So this part, whoops, that's not what I meant to do. This part goes away. And we end up with an exponent of 3/2 there. All right, so now we have the individual electric fields, but what we now need to do is find the total electric field. Okay, whoops, there we go. So now we simply have to take these two expressions and add them together. So let me take one of them and move it there. And now, or perhaps copy it, that will be better. So let me take one of them, just copy, paste, move, and this one, copy, paste, move. And we want to add them together, and this gives us the total electric field. Okay, so now what we can do is we can factor out a lot of things. So the total electric field, we can factor out this, we can factor out this. So we get 1 over 4 pi epsilon 0 times q divided by d over 2 squared plus z squared to the 3/2, right? Because it is here and there, so we can factor it out. And then we are left with this and this. So d over 2 in the x hat direction plus z hat minus d over 2 in the x hat direction plus z hat. So as we can see, the components in the x direction cancel out, while the components in the z direction, they add up. So the total electric field, 1 over 4 pi epsilon 0, blah, 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 q divided by d over 2 squared plus z squared to the 3/2. And then we have to consider that we have 2 times, so 2 q z hat. And that right there is the resultant electric field. Notice that I didn't simplify this 2 and this 1 over 4 pi epsilon 0. That is just convention. It's quite common for you to not simplify it. You can simplify it, it doesn't really matter. But often these 1 over 4 pi epsilon 0, they come up everywhere, so often they will cancel each other out, so it's good to have them there. But it doesn't really matter. So that is the first way of solving this. Now there is a second way, and honestly this is the way that I was taught in class, but I personally don't think that it is all that easy. So now the second way to solve this problem is a bit more geometrical. So what we do here is we just draw a little bit what is going on. So we know that this charge will produce an electric field that will go in this direction, right? They are both positive charges. So the electric field that results will go in this direction, right? So this is the electric field from particle 1 or charge 1. But the other charge is going to produce an electric field that goes in this direction. So E2. So the point of this method is to use the fact that we have symmetry in our problem, right? Both of these charges are the same distance apart from the point of interest, I mean, in the x direction. So the x components, because they also have the same charge, they will be the same thing because the electric field depends on the distance, and both have the same distance in the x direction, and they also depend on the charge, and both of them have the same charge. So that means that this charge that is doing a force, you can think of it as doing one part upwards and one part to the left in the negative x direction, while the other force from this one is going to do also a part upwards, which is going to be equally large as the other, and then it's going to do a force to the right or the positive x direction, which will be of the exact same size or magnitude as the one that's going in the opposite direction. So that means that this component should cancel out this one, while the vertical components or the z components will add up, giving us twice the result of just one of their vertical components. Okay, so what exactly do we do here? How do we proceed here? Well, the idea here would be to find, right, one of our electric fields in the z direction, because we know that the total electric field that we get from this entire thing is going to be twice the electric field of just one of them. It doesn't matter which one, let's just say EI, in the z direction. That is what we can see from the geometry. So how do we find just the z direction here? Well, we can see that this component here, right, if we take this, maybe let's get rid of some of these lines. So if we take this, maybe let's go for E1, for example. So this right here is just the magnitude E1, right? This is just the magnitude of the vector E1. And this here is going to be vector E1 in the z direction, while this thing here is vector E1 in the x direction, right? And this is a vector. You can, of course, also calculate its magnitude. So we have a right triangle. And what we now want to do is decompose our electric field E1 into its components in x and z direction. And well, we just want the z direction, so that's the one that we will keep. So we can see that there is an angle here. We don't know what it is. We can just call it theta. And in terms of that theta, we could write this as the E1z, the electric field due to charge 1 in the z direction. This is, now look at this drawing here. We know that the cosine of theta, right, just quickly here, cosine of theta, this is this side, which is the magnitude of E1z divided by the hypotenuse, which is the magnitude of E1. Or if you turn this around and you solve for this, you can find that the magnitude of E1z, which we already know goes in the z direction, this is going to be E1, its magnitude, times the cosine of theta. All right, but what is the cosine of theta, right? We made that up. We made theta up in this drawing, so we need to figure out what it is. Now for that, we need to use some more geometry, and this is why I think that this is not the best way to approach this, but it does also teach you a lot of things. It can be confusing, but you have to be careful and make a good, nice, neat drawing. Don't just sketch, because that's where you make mistakes. So if this is theta, now I make this line because it is parallel to the one down here, which means that now the angles that intersect are going to be the same. So this theta is the same as this one, for example, and this angle right here, which I don't know, call it alpha or something, is also the same as this one. Now, from this point, there's a lot of ways you can use alpha to find it if you want to do extra steps. But the most direct way is to just use theta. I wrote on alpha because I used to have trouble seeing it right away, and I did like a two-step thing using alpha and then theta. But if you just use theta and you see that this is a right angle, and you recall that this is z, this is r1, right? Then here, what is cosine theta? Well, cosine theta, the definition of cosine, right? Adjacent side divided by the hypotenuse. So the adjacent is z, and the hypotenuse is the modulus of r1. So we can now plug this in here. So here we get modulus of E1 times cosine, which is z r1. Okay, so that is the modulus of the electric field due to charge 1 in the z direction. Now, what is the modulus? Actually, I'm going to go down a little bit. So here. So the modulus of E1z, this is the modulus of E1 times cosine theta, which we just saw is z over the modulus of R1. Okay, so what is the modulus of each one of these individual things? Well, the modulus of E1, this is 1 over 4 pi epsilon 0 times the charge that is producing it, which is Q, divided by the modulus of R1 squared. And then we have still, and this is very important, notice this, because then we have R hat, right? But we want the modulus of all of this. And then we multiply by z over the modulus of R1 hat. Okay, well, what is the modulus of this? It may seem confusing, but that is the beauty of using this R hat notation, because that means that the modulus of this vector is 1, right? And this is a number. The modulus of a number is itself, right? The modulus of 5 is simply 5. So we can simply take all of these numbers, right? This thing is already a number because it already has this modulus, q divided by R1 squared, and the modulus of R hat is 1. So we don't have to worry about it. And then we have z divided by this thing, which we already have down here. So instead of having this squared, let's have it cubed. Okay, and now the final step is to write down that modulus. So we have 1 over 4 pi epsilon 0 times q times z divided by the modulus of R1, which we already found in the previous section, but we can just calculate it again if you want, right? It is simply the Pythagoras theorem, right? This thing squared, it is equal to this side, which is d over 2 squared, plus this side, which is z squared. So to find R1, we have to take the square root. Okay, so the modulus there is d over 2 squared plus z squared, and that is it. And this thing, of course, is cubed, right? So this is, of course, the same as writing this in a notation that I like more. You can stick to that notation if you want, just using 3/2, right? It is perfectly equivalent. And this is exactly the modulus of the electric field due to charge 1 in the z direction. But now we don't want the modulus, we want to find the actual electric field in the z direction, because we know that the total electric field is going to be twice this amount. Again, we could have done this calculation with the other charge, but it doesn't matter. I just use this one because, I don't know, I liked it more. So this is going to be this thing, right? Let's just do it like this. So this is, any vector is its modulus in the direction, but this is in the z direction. So of course the direction is z hat. So now I just need to write this down. So this is 1 over 4 pi epsilon 0 q z z hat divided by d over 2 squared plus z squared to the 3 over 2. And now what is the total electric field? Well, the total electric field, right? So the total electric field is twice this electric field. So it is simply this exact same thing times 2. So we take this and we just multiply it by 2. And there we go. We got the exact same result as using the different method, but I hope that this also helped you understand it in the geometric sense. One final thing we can do is just see what happens, to check if this is correct, see what happens if we change the distance d. So say, for example, we let d go to 0. What does that mean? That is basically saying that we put both of our charges one on top of the other, right? So you can imagine that this charge goes to our midpoint here, and so does the other one. So we end up with one charge that has charge 2q right underneath, right, our z-axis, pushing our charge upwards. So what would happen here? If d were to go to 0, our electric field, it would be 1 over 4 pi epsilon 0 times 2q times z divided by, and now this thing is 0, so we get z squared to the 3/2. Now this 1/2 cancels out that one, so we get z cubed, and we have z cubed here as z there, so we end up with z squared. And then finally, we still have z hat. And notice this. This is the electric field for a charge where Q is equal to 2Q, right? Here, Q being the usual notation that we use. And that's quite interesting, and it is precisely what we saw here, right? That's exactly what we would expect, right? Our situation is literally just one charge with charge 2Q, which is why, and it is the same situation that is represented right there. So there you have it. If this video was useful to you, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.